Noise evaluation is to use measurable and calculated indicators to evaluate the impact of noise on receivers and wearers' environmental conditions. The main factors considered in noise evaluation are noise intensity, frequency spectrum, duration, fluctuations with time, time of appearance, environmental conditions, human hearing characteristics, human physiological and psychological response to noise, measurement conditions and measures, etc. Commonly used noise evaluation indicators are A-weighted sound pressure level, equivalent continuous A-weighted sound pressure level, day-night equivalent continuous A-weighted sound pressure level, cumulative percentage sound level, noise impact index, noise criteria curve, noise reading curve, noise reading number, etc. The first, A-weighted sound pressure level. This indicator is the most widely used, reflecting the human ear's weighting of the loudness of different frequencies of sound, which can better reflect the subjective feeling of human beings, and can also correspond well with the degree of damage to human hearing by noise. The octave or one-third octave spectrum of noise can be converted to A-weighted sound pressure levels by calculation. State-steady noise can be evaluated by directly measuring the A-weighted sound pressure level. The second, equivalent continuous A-weighted sound pressure level. This indicator is to evaluate the fluctuating noise of the sound pressure level with time by using energy average measured over a period of time. The actual measurement mostly adopts equal readings. This indicator is widely used, but is sensitive to the appearance of occasional outbursts of high-level noise, because it does not contribute much to the noise energy over the entire observation time. The third, day-night equivalent continuous A-weighted sound pressure level. This indicator takes into account that the interference of noise to people at night is about 10 pascal larger than light in the daytime, and the equivalent continuous A-weighted sound pressure level for 22 hours a day is obtained through calculation. The first, cumulative percentage sound level. This indicator is used for the evaluation of random noise and represents the sound pressure level exceeded by the noise within n% of the measurement time. Commonly used, L10 presents the peak value of fluctuating noise. L50 presents the median value of the noise, and L90 presents the background noise. The fifth, noise impact index. This indicator is used to evaluate the scope of urban environmental noise impact. Considering that the affected population density is different due to different noise distributions, in an ideal noise environment, this index should be less than 0.1. The sixth, noise reading curve. This indicator is a set of calculation curves specified by international standards. It is proposed on the basis of the NC curve that comprehensively considers the effect of noise in three aspects: hearing loss, speech interference, and noises. Each curve in the figure is represented by a noise rating number. Sound presence level in 9 octave bands from 31.5 to 8000 Hz were determined. The sound pressure level of each octave band corresponding to N can also be obtained by calculation. Draw the measured noise octave spectrum curve on the NR curve and take the N of the curve that is closest to the noise spectrum curve and has the largest N as the noise evaluation number of the noise. The red line in the figure represents an N of 25 and the blue line represents an N of 50. You can also find N by calculation and take the largest integer as N. It is required that the sound pressure level of each octave band of the noise measured on site will not exceed the sound pressure level specified by the limited curve. Noise population is physical population. Noise prevention is mainly to control the output of the sound source and the transmission path of the sound, and to protect the receiver. The principles of noise control are: the first, control of the sound source. One is to improve the structure, improve the merging accuracy and assembly quality, improve the operation method, and reduce the noise emission power of the sound source. The second is to take measures such as sound absorption, sound insulation, reverberation reduction, and the insulation of mufflers to control the noise radiation of sound source. The second, control in the sound transmission path, mainly include through-site selection, keep noise source away from quiet place, control the emission or propagation direction of noise, set up sound insulation barriers to block the spread of noise, use sound-absorbing materials and sound-absorbing structure to consume sound energy in propagation, adopt reverberation isolation to reduce noise transmission, adopt reasonable urban noise prevention planning. The third, protection at receiving point. Wear ear protectors, reduce exposure to noise, regularly change stuff in noisy environment. The noise reduction effect of various measures is different. Updated equipped and its precise can gradually be reduced by 30 to 40 decibel. The sound absorption can be reduced by 6 to 10 decibel. The sound insulation can be reduced by 15 to 30 decibel, and the muffler can be reduced by 15 to 40 decibel. It can be seen that the noise reduction ability of sound absorption is limited. Noise measures should be reasonably selected according to relevant factors such as the cost of use, noise allowable standard, and work efficiency. The sound absorption and noise reduction method is to use the principle of sound absorption to arrange sound absorption materials or sound absorption structure on the ceiling and walls to reduce the reverberation sound. It is suitable for large space where the inner surface of the enclosure is made of hard materials and the reverberation sound is dominant. When the required average sound absorption coefficient is larger than 0.5, it is unreasonably economically, and other measures need to be supplemented. The calculation formula of sound absorption and noise reduction is derived from the calculation formula of indoor sound transmission. It is suitable for when the reverberation sound is main sound, and the sound absorption and noise reduction amount is about 0 when direct sound is main sound. It should be noted that when calculating by room constant, average sound absorption coefficient, and sound absorption, it is the ratio after treatment and before treatment, and when calculating by reverberation time, it is the ratio before treatment and after treatment. Let's do an exercise. It is known that the length, width, and height of the workshop are 10 meter, 20 meter, and 4 meter respectively. The surface area of the pipeline is 24 square meter. The surface area of the machine is 20 square meter, and there are 4 people. The sound absorption coefficient of the ceiling, ground, and wall is 0.02. The sound absorption coefficient of the pipe surface is 0.5. The sound absorption coefficient of the equipment surface is 0.02, and the sound absorption of one person is 0.42. The ceiling is to be affixed with a material with a sound absorption coefficient of 0.8 at 1000 Hz. Find the amount of sound absorption and noise reduction at this frequency. Since the sound absorption coefficient before and after treatment is known, the sound absorption before and after treatment can be obtained separately, and then substituted into the calculation formula of sound absorption and noise reduction. The calculation results of sound absorption are listed in the table. Since only the ceiling is presided, the sound absorption after the treatment is only increased by the ceiling. The total sound absorption before and after treatment is 26.9 square meter and 182.9 square meter respectively. Substitute into the calculation formula of sound absorption and noise reduction and get 8.3 decibel. It can be seen that the ability of sound absorption and noise reduction method is limited. Think about it. What if the audible noise standard is not met after the sound absorption treatment? How to judge whether the sound field is dominated by reverberation sound or direct sound?